Hello, welcome to this video. So in the last video, we are trying to find dDelta PDRE. Okay, that is for the calculation of Jacobians, which we want to get. So this dDelta PDRE is the critical one. However, my way of doing it is to convert everything into a non-dimensional form of the equation, so that we can do away with unit errors as far as possible. And I said in the last video that we use the Bijon number, okay, because I don't want to reinvent new dimensionless quantities. So okay, you see all of these things. Okay, here's the fanning friction factor. This one's fanning, not any other friction factor. So it has a after a lot of these simplifications, we have a 4L by D ratio over here, 32 times of the Bijon number, and then so on and so forth. Okay, so FRE times RE squared equals to 32 Bijon number divided by 4L over D cubed. Okay, so if we move all of these 4L over D cubed terms and the 32 term to the left hand side. Okay, let me see. Yeah, if I'm speaking clearly, should have enough volume. Yeah, if I move all of these terms to the left hand side and then we just use a numerical algorithm to differentiate this, then you will be able to easily get dBE dRE. And to get the dDelta PDRE, and this is the desired term here, we get the dDelta PDRE term. Okay, so we make this a subject and then we just shift everything here to the left hand side, and we should be able to be fine. Okay, so yeah, this is how we can first find the dBE dRE. Okay, so this is the term on the left hand side. So dBE dRE is, okay, all of these things here. All right, we differentiate both sides by the Reynolds number. So d by dRE of FRE times RE squared. So this, you'll see this derivative pop up over and over again in the functions. And now, of course, these constants, we can just bring it over to the right hand side. Okay, so this one, all of this following here is like the analytical method of doing it, which I will not include because there are already like MathNet derivatives, and I think it's kind of a bit of a time wasting endeavor unless it really speeds up the calculation time, which it doesn't. I mean, it doesn't justify me trying to what do you call that? It doesn't justify all the tests that I need to do to make sure this code actually works. After all, there are a lot of careless mistakes that can happen when I do these many steps. And indeed, I could not get it to work properly. So I just stuck with numerical derivatives. So here is the equation we are left with. This FRE times RE squared, and then FRE here, this is a fanning friction factor. I will just use the Churchill correlation in order to get that part done. Okay, so that's how I do it. Okay, so Churchill friction factor, we already sort of got it. Let me go to other terminals. Tab new, nerd3. So the Churchill friction factor, we already can get it. Okay, Churchill friction factor, we already can get it. It isn't too mathematically complex. I have a oops, undo that. I have a Churchill inner term, an A term, a B term, and A and B are, as we can see over here. A and B. Again, we can see over here what A and B is. I'm not going to go into that. So this is the code to calculate Churchill friction factor. Okay, and I'll just skip this part. And then the code to calculate the derivative is here. Okay, calculate fanning partial derivative. So that is considering that roughness ratio is constant. Then let us calculate the fanning friction factor. So this is the code that I use here. I use a virtual indicator, not to really complicate things unnecessarily, but in case I want to find other ways of calculating this friction factor, I can do so. Okay, so this is the constant roughness fanning thin constant roughness fanning. So this actually calculates the fanning partial derivative. So it's d fanning dRe. Okay, so this just calculates the dF dRe, not the current balance F, but this F fanning dRe. Then of course I use some product rule to get the total derivative right here. That's one way of doing things. All right, that's one way of doing things. Okay, so this is what we get. Okay, and then I use some sort of derivative object to calculate it. Here's the central difference class. So it's an in-house class I made. I did not use the MathNet class. But if you go all the way to the bottom, there should be a version that uses the MathNet version. So this class here is the one I'm actually using, Churchill MathNet derivative. So I make this derivative object, and I use a similar method. I have a function in here to calculate the fanning friction factor, but this time this is just based on the Reynolds number. Okay, the roughness ratio will be put into a class variable, and this will not change when we calculate the partial derivative. Okay, so this is where we calculate the partial derivative using the MathNet class. Okay, go and read that up how the source code works. I will not be explaining it here. Okay, this will be under math. You go into derivatives, and then you will see this MathNet derivatives.cs. This will be using the MathNet libraries, which are already tested, so I don't have to make my own partial derivative classes or central difference approximation classes. So all of this is done here to calculate, okay, the fanning partial derivatives. Okay, so once the fanning partial derivatives are done, we can finally try to get our Jacobian straight away. So this is the dF dRe squared. Okay, there are again few ways of doing it. Okay, there are a few ways of doing it. Oh, where am I in this? Churchill friction factor. Oh, yeah. All right, yeah. So this is the Churchill friction factor class, just to make the Churchill friction factor. I make this a partial class here because I wanted to add different functions into this Churchill friction factor class, so that you know, I can when I split it up, it kind of becomes somewhat more organized. Okay, but there's a reason I kind of put the rest of the functions under here in the Churchill friction factor partial derivative class. Okay, so here I have yeah. So I have this fanning friction factor. Yeah, this fanning friction factor term. I also have my inner term right here. Okay, I have my A and B terms. Yeah, this is very strange. Why do I have two classes? Churchill friction factor. It looks almost like a duplicate to me, but let me take a look. All right, here are classes used for the partial derivatives only. Oh, right. So okay, this is the friction. Yeah, I was trying to look at the friction factor for Jacobian, but this is the friction factor just for calculating A and B, not the Jacobian. Yeah. So these classes actually contain this class actually contains the vanilla Churchill friction factor. I just use it to calculate the A, B, and the fanning friction factor from the Churchill correlation. Here's the one for the derivatives part, where I have Churchill friction factor sort of also being a mega class here. This is a mega class that also satisfies the I friction factor derivatives interface. So what you have here are methods of functions to calculate the Churchill friction factor partial derivatives. Now the Jacobian here is where we calculate the actual, of course, Jacobians. Okay, so we start off with the dBdRE. So this is the part where we actually calculate the Bijon number thingy. Okay, the Bijon number. Okay, we see this dBdRE, dBedRE. Here is where we are. Okay, so dBdRE. And this is where we are calculating this particular derivative here. And first thing first, of course, is we receive a length to diameter term. Okay, a length to diameter ratio, length to diameter ratio. Then we are trying to calculate the length to diameter term. Length to diameter term is this 4L over D cubed. Okay, I just have a function to calculate that all together, so that we can start ourselves off. Then we have our derivative object. Okay, we make a MathNet derivative object. Okay, to do our central difference approximation. We have a roughness ratio right here. So what I'm doing here is that I'm assigning this roughness ratio variable to a variable in the class, so that we can actually calculate the fanning times RE squared. Okay, look at this. We're actually trying to differentiate the fanning friction factor times the Reynolds number squared. So this is exactly what we are doing here. So this function just returns the fanning friction factor times the Reynolds number squared. Okay, just the fanning friction factor and the Reynolds number squared. Doesn't do anything more than that. Right? This is of course the first iteration. You'll find out later that this kind of thing has a problem. Okay, when I actually try to run it. But supposing things are okay, we can just calculate a derivative result right here. Okay, this is our derivative result, which is using the derivative object calculator. We place in this function or method, constant roughness fanning RE squared. So this is the method we are using. Okay, this method we are using. Then we want to differentiate it with respect to the Reynolds number. Then after we are done calculating, I'm going to set the roughness ratio within this class back to 0. And then, okay, the derivative result of dBdRE, it will be this derivative result here. It will be the dFdRE squared, and then I have to multiply this 4L over D cubed. Okay, 4L over D cubed. So the times equals there is to multiply 4L over D cubed, which is this length to diameter term inside, and then I divide it by 32. Okay, you see this 32 right here. Okay, once I'm done with this multiply and divide part, I return the derivative result, and then I get this dBedRE. Okay, so once I have this dBedRE, it's relatively okay. We should be able to find dPdRE. So let's look for dPdRE on over here. In this case is dDelta PdRE. Okay, I name it dDelta PdRE because there's obviously a change in pressure. It's a pressure drop over here. So let's look at dDelta PdRE. This will take in a Reynolds number, roughness ratio, length to diameter. Okay, and objects like the length scale. Okay, why do we need a length scale? Well, the length scale is there because we need to calculate our L over D. Okay, so we need a length scale, which is the L thing, and a length to diameter ratio in order to calculate our L and D, that kind of thing. So yeah, and of course we also need this dBe d delta P. dBe d delta P. So if we differentiate this whole thing here with respect to delta P, okay, we will need the length scale, which is this L, and of course the kinematic viscosity as well, which is the nu squared, or nu. Okay, of course I will square both the terms, but the important thing is to have this L squared and nu squared to find dBe d delta P. Okay, so we find dBe d delta P, so we differentiate this equation both sides by delta P, so we'll just get L squared and nu squared. So that's why I'm having these two things right here. Okay, so So that will be how we find dBE dΔ P. Okay, so first thing first, over here I'm converting everything to SI units. So length scale equals length scale to unit length unit or SI. Nu equals nu to unit kinematic viscosity unit dot SI. Alright, so that makes it a unit sort of safe. Like I convert everything to the units, convert everything to SI units. Next thing is I need to make the derivative result. Okay, so this dΔ P dRe has units of specific energy. Okay, this thing has units of specific energy. Okay, if I'm not wrong. Oh, dΔ P. Yeah, oops. Yeah, dΔ P dRe, it will have units of specific energy. Why? Because I'm actually dividing it throughout by dBE dΔ P. So dBE dΔ P has L squared over nu squared units. When I flip it around, it becomes a specific energy unit. Okay, so this is the final result. This is the final result for dΔ P dRe. Okay, so this is just like the unit conversion bit. So I will have an intermediate unit result first, which is nu squared. Okay, nu squared. So this is nu dot power 2 over the length scale to the power of 2. So this is the nu squared over L squared, because I'll have dBE dΔ P. Okay, dBE dΔ P. But what I need to do is to make dΔ P dRe the subject is to switch this, bring this over to the left hand side. So I will change the side. So nu becomes on top, length scale becomes at the bottom. Okay, so this is the intermediate unit results with the correct units, nu squared over L squared, and this intermediate unit result, I will multiply it by this dBE dRe. So the dBE dRe is this code here, which we just discussed, that calculates the dBE dRe derivative. Okay, the dBE dRe derivative. Yeah, and then what's next? After that, I will take this intermediate unit result and cast it into a specific energy unit. So this is just a typecasting for C#, and I won't go through that. I will just assume you know how to typecast things properly. Then I will just return the derivative result. And voila, we have a dΔ P dRe term. So that is the most of the work actually already done. So once we have the dΔ P dRe, what can we do? We can actually substitute it back into this equation. Okay, and we just need two more derivatives, dΔ P dPA or dΔ P dPB and dmPipe dRe. Okay, so the first thing I have here is the dmdRe, which is over here. Okay, dmdRe. How do we find dmdRe? Okay, we find dmdRe by looking at the same equation here. Okay, we look at this. That's the equation. Go down a little bit. Yeah, dmdRe. Yeah, I will just swap this equation around. I'll bring mu and A cross-sectional area to the left-hand side and D to the left-hand side. Now differentiate both sides by Reynolds number. Okay, I assume Reynolds number only changes due to velocity and maybe kinematic viscosity, but we assume that kinematic viscosity doesn't even change much when we change the pressure. So all of this, diameter, viscosity, cross-sectional area, they are essentially constant. And I'll just differentiate with respect to Re, assuming all of these are constant. So for that, we need to, for that quantity, dmdRe is actually mu times A cross-sectional area divided by D. So what do we have first? We have our cross-sectional area, fluid viscosity. So this is a dynamic viscosity. Then we have our hydraulic diameter, which is the D. Yeah. And then after that, we do our appropriate math. I will just call this the intermediate unit result. And all of these will be in mass flow rate units. And then what I'll need to do is to get this derivative result and cast it, use the intermediate unit result, and I'll cast it into a mass flow rate form. And then I will return the derivative result. This is how I get the dmdRE. Okay, and the last part is just pressure. Okay, let me find the pressure for you. Okay, the last part is just to find the dDelta P dPA or dDelta P dPB. So I just assume that the pressure is kind of they can be varied independently. So delta P, I will use PA to differentiate both sides. So if I do dDelta P dPA, then PB will just disappear, and then I will just get 1. dDelta PB dPA is 1, and at least the partial derivative is 1. Okay, that's assuming they vary independently. Okay, so that's how I get the 1 here. And likewise for the delta P dPB, so that means I differentiate this equation both with respect to the pressure at B, kinematic pressure at B. I assume A is independent of B, so this thing kind of just drops to 0, and this term becomes -1. Okay, so that's how I get the -1 here. And voila. Okay, I have all my 3 terms here: dΔ P dPA, dmdRE, and dΔ P dRE. I should be able to get my Jacobian terms here, dmPipe dPA. So where's the dmPipe dPA? Okay, so this is one example, dmPipe dPA. All right, so this is how it is. I will need the cross-sectional area, dynamic viscosity, hydraulic diameter, Reynolds number, roughness ratio, pipe length, fluid kinematic viscosity. These are all the data that you kind of need. It's a lot of inputs, but yeah, I will keep it that way. It's kind of explicit. It tells you what you need. Okay, at least for this iteration, I don't overcomplicate the code design. So okay, first thing first, I will just calculate dΔ P dPA. Okay, so dΔ P dPA is over here calculated. I will calculate the dmdRE, the length to diameter ratio, and then I will feed it into the dΔ P dRE, and then I will multiply, divide, whatever accordingly. Okay, and of course here I will need my Jacobians to be in a double, because the biasing behavior code, it needs a double. If you take if you take a look later, you can go and find out. But yeah, we need it to be in a double form. It cannot be in a unit form anymore. However, what I'll do is this: I will just convert all those units to SI units. I will make sure all those units are SI. That's why I have this S code here as mass flow unit or SI. This will convert everything into a double, which is just decimal, or double numbers, floating point numbers, and then I will just return it into the back to the code, or rather, whoever uses this function, it will just be that, deliver it back that. Okay, so the dmdPB is the same. Okay, the dmdPB is the same. So this is how we do it. Okay. Okay, and this okay, and of course you think that everything is okay now. We have an explicit function that uses a Reynolds number and everything to calculate the dmdPA. Okay, but there's a slight problem with that. If you take a look at the biasing behavior, okay, we will not have any sort of Reynolds number to start us off with. Okay, what we usually start us off is a pressure drop. Oops, okay, this is the wrong class. Let's go for biasing behavior here. Yeah, this is the biasing behavior of BasePipe. So this is the correct one. Okay, so under biasing behavior load, okay, we have to have our the first thing we kind of start off is we start off with an initial guess of the potential difference or pressure drop. Okay, we start off with a pressure drop. Okay, so we don't start off with a guess of the flow rate, we start off with a guess of the pressure drop. And from that pressure drop, you're supposed to guess a flow rate. Okay, we're supposed to guess a flow rate from that pressure drop. Okay, so we need to find some of the roots later. So we get a flow rate from that pressure drop, and we are supposed, if you want to calculate let's say all the Jacobian terms. So I'm going to skip all of this stuff. dmdPA, for example, I need to be able to use pressure drop as an input rather than just, okay, I calculate the Reynolds number over here explicitly. I just want to be able to fit pressure drop into this function, and it will just give us the Jacobian as well. So there's a little bit more extra work to do because we have a pressure drop, and we need to use that pressure drop to guess the Reynolds number and then solve for it. So how can we do it? Okay, if we I'm going to go B# to go to the last buffer. Oh, okay, let me go. Where's the let's see, buffer pipes.readme, no, churchillFrictionFactor jacobian.cs. Okay, that looks like the one. So so I don't need to look for buffer numbers, but yeah, I can open the exact file that I want. What was I looking for? Yeah, I was looking for yeah, the thing to help us with this problem. Okay, normally we need a Reynolds number first to actually get the Jacobians, and that's fine. However, we don't always have a Reynolds number first. In our case, we have a pressure drop difference. So this, I actually made an overload here. Okay, I made an overload here which actually takes in the pressure drop, and what it does is to convert that pressure drop into some sort of a Reynolds number guess. Okay, it will guess the Reynolds number. So first thing first, I will of course take in all these arguments. First thing first, I will get is a Bijon number. Okay, I will get a Bijon number, and once I get the Bijon number, I will calculate the length to diameter, and then I will calculate the Reynolds number here. Okay, how do I get the Reynolds number? It will be using this class, but I use the get Reynolds number method, and this is just how do we do this? Okay. Okay. Yes, here's the get RE class, which is inherited from the churchillFrictionFactor class. So this is the class I'm using here. So this is the get RE class. Okay, this thing over here, just ignore first, because I had problems for when the Bijon number is 0, meaning to say there's no pressure drop. Then this code, this behavior will just get wonky, very wonky. So meaning to say that the Reynolds number will be something like infinity or something, or I don't know, some undefined number which it cannot cope with. Okay. So okay, this is how the get RE function works. The whole purpose is to get a Reynolds number from the pressure drop. Okay, so we have a pressure drop root function, and I'm going to use a root finder. I will use a root finder, and this is actually within the MathNet class. Okay, the MathNet class or MathNet library. You just use the find roots of function. Okay, so you just apply a function. You will try to find the root. Okay, so the function must be a one input, one output. So that's why the input here should be Reynolds number. The output here is, well, whatever this thing is here. Okay, what I want to do is to make this function 0. So how does this function work? Let's look at the underlying equations here. Okay, so the underlying equation here is, I believe, let's see. yeah, the underlying equation will be this equation here. Okay, what I'll do is I will supply a Bijon number and all the other terms. And with a Bijon number, I'm supposed to find the Reynolds number. Okay, so this is the Reynolds term here, and this is like the Bijon term, which is 32 BE over this length ratio here. So I have this Bijon term, okay, 32 times the Bijon number, and then I multiply it by the 4 times the length to diameter ratio to the power of -3. So this is 4L over D to the power of -3. You can of course put it in the denominator, that's fine. I just choose to do it this way. Okay, so this is the Bijon term here. So I'm basically making it such that the fanning term minus Bijon term, I want to equate it to 0. So this is the fanning term, this is the Bijon term. I want to subtract both sides by this, and then on the right hand side it should be a 0. So when that equation is 0, I'm essentially finding the roots. Okay, I'm essentially finding the roots. So this is the pressure drop root thing, and over here I have the fanning term right here. Okay, the fanning term is, okay, I'll calculate the fanning friction factor based on the Reynolds number and the roughness ratio. Again, I use the same trick of putting this into the class variables so that I can put it here. And then I will multiply it by the square of the Reynolds number, and this is what this line is doing right here. Fanning term times equal math power Reynolds number to the power of 2, and this is what we are doing right here, FRE times RE squared, and that will be the fanning term. So and I want to find the equation, and I'll return of course the fanning term minus the Bijon term, and I'll try to find the roots here. Okay, so the Reynolds number is here. I will try to find the roots of this equation right here. Okay, I'll try to find the roots of this equation right here, which is find roots of function pressure drop root between Reynolds number 1 and Reynolds number 1 times 10 to the 8. Okay, and of course you see when Reynolds number drops to 0, I cannot really do anything. So that's what we are kind of stuck with. Okay, so I mean whatever, so it's fine. We'll just live with that for the time being. Okay, because as you know, fanning this the Churchill correlation, fanning friction factor kind of shoots off to infinity as we get closer and closer to 0. It's not a well-behaved function. Okay, and you'll see that if we just chuck this code in, we will actually get errors. Okay, they will actually get errors which I have to debug. But anyway, we take this function and we get a supposed Reynolds number. Once we get the Reynolds number, I set all the inner class variables to 0, and then I will just return the Reynolds number. And that's how we get the Reynolds number from the Bijon number and everything. Okay, so let's go B#. Okay, so this is how the Reynolds number part is gotten. And then I will have the derivative result, the derivative result will be, I will just use this function, this dot dmdPA. Okay, means to say I will be calling this specific function right here. Okay, with all the work done. Okay, this dmdPA using the Reynolds number as an input. And then I will calculate things out. And then I will return the derivative result as a double. Okay, so this is how we calculate the dmdPA and the dmdPB. Okay, so yeah, this one's the one using the pressure drop. And these are the only overloads I kind of need now. So I'm not using anything else. And let's go back to the biasing behavior to see how these are used. Okay, so the biasing behavior part is here for the base pipe. And then you see I'll use all these functions here with all the thought put in there to calculate our Jacobians. So you can see there are 4 Jacobians terms here: dmdPA, dmdPB, minus dmdPA, and minus dmdPB. Okay, why do I have all of these? Okay, you will see that I need 4 Jacobians. Okay, you just go and look at that part. Okay, in the theory. All right, so this is that part. Okay, so I think over here I might need to actually correct some code. Okay, yeah, but this is what we are doing with the derivatives here. Okay, and then of course I kind of followed the order of the what do you call that? The same spiceSharp solver. I actually give it some sort of G minimum. Okay, G minimum. So yeah. We have a minus dmdPA, minus dmdPB. Right, I don't know why. Yeah, this one looks a bit fishy to me. I'll probably sort it out later. But yeah. Yeah, this thing is something I need to sort out. Probable error. Okay, so what is this part doing? It's in case any of these derivatives are 0. For the first round, we do not want the derivative to be 0. If not, we have a so-called singular matrix when we cannot solve for anything. Okay, so here's to make sure that these values do not actually go to 0. Okay, so yeah, this is what we can do. Okay, the dmdPB and the dmdPB, there will be a math-max function used here, and what happens is that, yeah, this math-max function is okay. If this what is trying to do here is, if this value goes to 0, we will actually use some sort of minimum for the Y matrix. It's a very small value just above 0, so that we can actually solve the matrix. It's a numerical thing to help convergence. Okay. However, the negative part here, if we use the math max value, we'll kind of get some sort of error. So we need to do something about this. Okay, so what I'll do is I'll do a minus sign here, so that this minus thing is a positive value. Okay, so the maximum of the dmdPA, because the minuses cancelled out, and the base config G minimum here. I'll have these two things here. I leave it out, and then what I'll do is I'll just add a minus sign in front. Okay, and that should actually make the code correct. Okay, it will do the same function as the above. All right, so this one is if the voltage was reversed, reverse the current back. I just copy and pasted the thing for mass flow rate. And actually, I also didn't tell you how I got those mass flow rates and everything. So this is how I get the what do you call it? This is how I get the minus the dmdPB and everything. I need cross-sectional area, fluid viscosity, blah blah blah. Okay, so the absolute roughness, I get it from the base parameters. Actually, I hide it all within here. I have hydraulic diameter, pipe length, absolute roughness. I have functions for cross-sectional area, roughness ratio, length to diameter, kinematic and dynamic viscosity. So that's how I get all these values. Okay, and this is just legacy code which I can delete. And those are part of the non-linear resistor part, which they are not important. I just left them there as a reference. So okay, I get the Reynolds number. Okay, Reynolds number here. If Bijon number is more than 0, then I will get this Reynolds thing. Okay, why do I have this? It's because yeah. Okay, never mind. Let me show you over here where I get all the cross-sectional area and everything else. So cross-sectional area, mass flow rate, everything will be gotten from. Okay, these three terms here, they'll be getting from the base parameter. Mass flow rate, okay, the mass flow rate will be dmdRe times the Reynolds number. Okay, so mass flow rate is the Jacobian object. I get the dmdRe term, and then I get the Reynolds number right here. Okay, it's not the most efficient computationally speaking, but it does the job. Okay, because I call this dmdRe function multiple times when I'm getting the minus dm. When I get these four derivatives here, I actually calculate it again and again, and I'm actually using all these functions here with I'm using the same functions 4 times, which is nice when it's explicit. It's clear to the reader what's going on, but it's not the most computationally efficient. But it gets the job done. Okay, so yeah, I get all of this. I get the dmdRe. Okay, because dmdRe is what's dmdRe to get the mass flow rate? Yeah, dmdRe is right here. Okay, dmdRe is right here. Where is it? Yeah. Well, you can get it from this equation. You'll notice that dmdRe is just mu A cross-sectional area times d. Okay, if I want to get the mass flow rate, I just get a Reynolds number times mu cross-sectional area divided by d. So dmdRe is mu area cross-section divided by d. This is a very, okay, honestly speaking, this is a cheap computation. Then I multiply by the Reynolds number. Okay, and how did I get the Reynolds number in the first place? Okay, I get Reynolds number using the getRe function. This one's a bit more computationally expensive. We use the getRe function that we discussed just now to get the Reynolds number based on the Bijon number. Okay, this Bijon number here, and this Bijon number here will be, okay, I will use the get Bijon number function, okay, based on the pressure drop, fluid kinematic viscosity, and pipe length. Yeah, that's how I do it. Okay, so all of this is okay, but usually when we start calculations, all the values at node A, node B, all the pressures will be equal to 0. Okay, that's what I found out when I started. So that is a problem, because when we have a 0 pressure drop, and then our whole way of calculation will be haywire, because these functions do not behave very well at pressure drop equal to 0. Okay, so then you get specific energy is pressure drop. I'll convert it to the correct units, and then I want to start calculating the Bijon number. Okay, so at the Bijon number here, I say if the pressure drop, okay, if the pressure drop value is equals to 0, I will just arbitrarily give the pressure drop to some non-zero value. In this case, 100. Okay, it's just an initial guess, but it at least gets us out of the. It will get us out of the zone of, you know, it will get us out of the zone of the 0 zone, right? Okay, so this is how I actually so-called combat that near to 0 error where, you know, derivatives and Jacobians are not defined and the whole solver doesn't work. Okay, so now let's take a look at the results. Okay, so the results are over here, and let me search for BasePipe. Okay, so we have a reference mass flow rate. Let me restart this. Let me exit, or maybe I'll just okay, .NET watch test logger console verbosity equals to detail. See whether the code works. cd test and bang bang. That means this is the last command used. Oh, okay. cd test and ls. That's not very helpful. Okay, this is what I want. Okay, BasePipe. Everything seems to go well. Okay. Let me test again. Because I want to search for the right one. Okay, let's look for BasePipe. Yes, okay, so here it is. Mock pipe without using pipe factory. Here's our reference mass flow rate. Our reference mass flow rate is 3660 kg per second. Okay, when I switch, and how did I do the test? Okay, I'll go I'll go open the tests here. This is the pipe and valve test. Okay, this is how the test code goes. Okay, I will just have this base pipe here, which I call mock pipe. Okay, this mock pipe object over here. Okay, and I'll have a pressure drop minimum. Okay, this pressure drop minimum, I will try and calculate a Bijon number from it. Okay, so this is the reference, how the reference is getting done. Get a Bijon number for it, and then I'll get the Reynolds number from it. Okay, once I get the Reynolds number from it, okay, using the Jacobian object get Reynolds number, and this will be the friction factor Jacobian. Okay, I will then get the mass flow rate here, and this is how I get the reference mass flow rate. Okay, I will use all the codes from the original friction factor object to calculate a mass flow rate. And once I get the mass flow rate, I will say the reference mass flow rate is this much. Okay, so you can slowly go and look at the code, and this is where I get the mass flow rate is 3660 kg per second. Okay, and after that I do a DC sweep. Okay, meaning to say I alternate between two pressures. Okay, first is I'll have the pressure at pressure drop minimum. Okay, this is actually the pressure drop minimum right here, 1.45 meters square per second square. Okay, over there I don't have units because we need to use doubles. Okay, we need to just put in numbers without units. If not, the thing won't work. Okay, and this is the minimum pressure drop. This is maximum pressure drop. This is the interval between, and then it will keep doing steady states. Okay, and over here we have our pressure drop value. Okay, format it as a string, and after that we just do some cleanup and we're done. Okay, so you see that the pressure reference mass flow rate is this much. Okay, and then we'll see that this base pipe verification for the same pressure drop, we get very close to 3660 kg per second. Okay, so this is how I verify that it works. Okay, so that's how we do it, and maybe figure out some way to actually make the units actually make more sense. But yeah, this is how the base pipe actually works. Okay, so I'll stop for now. I'll see you next time. Bye bye.